Okay, let's talk about coplanar forces on a particle. So, we have a particle. We could have any number of forces on it. Situation like this. Here, we have a coplanar situation with 4 different forces on this particle. Notice the force 4 is pointing in the opposite direction, pointing towards the particle. These other 3 pointing away, just arbitrarily drawn on a Cartesian coordinate system. Well, each force has 2 components, 2 mutually perpendicular components, for example, F1, we've got this component, and then we've got the Y component. We got the X component, we got the Y component. Again, for F2, you have an X component and a Y component. For 3, a different X component and a Y. Sorry, I sneezed, had to mute component. And then F4, we have we can do it this way, a Y component in this direction, and then we have an X component in this direction. So if with all these forces on it that we can break down into all these components, if the particle's not moving, that means that the sum of our forces, the vector sum of our forces, almost equals 0. So we could continue. I could continue to write this as the sum of the x components in the I direction plus the sum of the y components in the j direction. So what this means then is that we have the sum of all our components in the x direction must equal 0, and the sum of all our components in the y direction must equal 0. And this essentially is section 3 in our textbook. Let's look at an example. Okay, so I have a mass suspended from 2 points. Let's call this a point A and this point C. They come together at this point B. And we could say this attaches to the mass here, D, if we wanted to. Okay, so our mass has a weight when it interacts with gravity. So mass has a weight of 588.6 newtons. Let's find the tension in AB and BC due to this weight. Okay, well, let's start out with our free body diagram. Okay, I have force in this direction. We'll call that tension in C. Going around clockwise, I'll just do that. I have the weight, and we'll probably want to put this on our free body diagram, what the weight is. It's a force, 588.6 newtons. And then I come back and I have tension in this cable. Remember, these lines can only hold tension. They can't hold compression. So I'm thinking this has tension this direction. Okay, now some of you are probably screaming at your screen saying, hey, this force should be in the opposite direction. Well, the reason I drew it that way, I drew it in the wrong direction, is because you're not always going to be able to tell as easily as your intuition is probably leading you down that path right now when you draw free body diagrams. But it doesn't matter. As long as you have the force in here, it doesn't matter. It will, when we do our calculations, if this TA, force in TA, turns out to be negative, I'll know that the force on this particle is in the other direction. So now I neglected to put some dimensions on here. So this is a 3-4 slope. And this guy from the horizontal is at 45 degrees. So let's transfer those dimensions to our force free body diagram. 3, 4. That means this is 5 over here. So this is a similar triangle. Little mini similar triangle represents that situation. And this one over here is represented by 45 degrees. Okay. So when you're in a problem like this, maybe you don't know where to start. So one of the first things to do is just sum your forces in the x and the y direction. So let's do that. So sum forces in the x, we know they're going to equal 0. And in the x direction, I have a force due to this, a force component due to this force, and that force is going to be proportional to 4/5 of TA. And then I add to that force here in the x direction, which is going to be TC cosine of 45 degrees. Okay, let's do our y direction. Okay, now we have a component here, and let us assume that we have y positive up, x positive in this direction. So some forces in the y then is going to lead us to -3/5, and it's pointing down, so it's going to be -3/5 TA. And then this component is going to be pointing up, plus, or the TC component is going to be pointing up. I guess you can't see my arrow when I'm using the pen. So it's going to be TC sine of 45 degrees. Finally, we have 588.6 newtons pointing down. Okay, well, so as I scoped the situation out, this turned out to be a pretty reasonable problem. We have two equations now, two independent equations, and we have two unknowns. So we can solve this system of equations for TA and TC. First, let's solve this in terms of TA, our summation of x. So I have TA equals minus 5/4 TC cosine 45 degrees. Just did a little algebra there. Okay, so now I'm going to take TA and I'm going to plug it into this equation so I can get an equation in terms of only one variable TC. So this equals -3/5 times TA, that's this, times minus 5 force TC cosine of 45 degrees plus TC sine of 45 degrees minus 588.6 newtons. We cancel here. Continuing on, this is going to turn positive now, so this equals 3/4 TC cosine of 45 degrees plus TC right over here. TC sine of 45 degrees is really going to be equal to the cosine of 45 degrees. So I'm just going to write cosine 45 degrees here. And then I'm going to set this, multiply by 1 or 4 over 4. So I can just do this addition real quick. Minus 588.6 newtons. So this equals 7/4 TC cosine 45 degrees minus 588.6 newtons. So therefore, TC equals 588.6 newtons divided by 7 times 4 over cosine of 45 degrees. You could have done this as sine 45 degrees if you wanted. And this equals, okay, so since TA is negative, we have drawn TA backwards, and TA should point in the other direction. So TA equals 420 newtons, and TC equals, I'm going to round this up 1 decimal point, 575.7 newtons. There we go. We could actually, should actually attach some arrows here. And then this one points in this direction.